smell bad, they stink. So that skunk smell is actually from a thiol. So like I said, most thiols stink. This one actually smells like coffee. Here's another one. Guaiacol, which gives this phenolic, spicy smell. So what function do you think is in guaiacol? Yeah, alcohol again, so the OL. This compound, 2,3-butane-dione, has this buttery smell or buttery taste. And what function group do you think is in 2,3-butane-dione? Yeah, ketone, so the ONE suffix is a ketone. And then last one is chlorogenic acid. This compound stimulates stomach secretion, actually secretes more HCl, and that's why coffee can give a person an upset stomach, because it increases stimulation of HCl in your stomach. Okay, so this is an acid. So in lab, just to review, we learned how to make a stronger cup of coffee. So you did that by finding a solvent in which the caffeine and other substances are soluble. The solubility of these substances depend on what? Well, that's what the extraction, but the solubility is a property of the substance. So what does solubility depend on? Yeah, so solubility, see for Chem1A, we can say that solubility depends on polarity and that light dissolved light rule. But in Chem1B, it depends on the type of solute. So if you have a molecular solution, solubility depends on versus an ionic solution. So this depends on George? Ion forces? Yeah, intermolecular, so yeah, intermolecular forces. Whereas in an ionic solution, solubility depends on so hydration energy versus lattice energy. So these compounds here are, would you expect these to be ionic compounds or molecular compounds? These four compounds in coffee. Yeah, so they're going to be molecular. Okay, so organic compounds are molecular in general, which means that the solubility of those compounds depends on so intermolecular force. Now, since those compounds are soluble in water, which intermolecular force is going to exist between those compounds and water? Yes, it's going to be hydrogen bonds. Okay, and then what you did is you did a solid liquid extraction to extract those solids from, or those substances from the coffee. The other thing you did is you wanted to measure the amount of the coffee you extracted from the bean. So one way to do that was to measure the boiling point based on boiling point elevation. Another way was to remove the solvent and then measure the mass of the solid residue left behind. The third way is, and a lot of you do it this way, is to measure the intensity of the color by UV visible spectroscopy, knowing that the amount of light absorbed is directly proportional to the concentration of that chromophore, that is the substance which causes the color. Okay, so that's what you did in part A. Then you're working on part 2, or part A, step 2. You wanted to make decaffeinated coffee, so you can extract the caffeine only from coffee by using a solvent in which the caffeine is soluble, but the other substances aren't. So you found that you could use benzene, which is a carcinogen, so we don't really want to use that. Or chloroform, which is a mutagen, we don't want to use that. Chloroform used to be used as an anesthetic to knock out people. They don't use that anymore. Methylene chloride is also a carcinogen, so you don't want to use that. But ethyl acetate, that's been used in fingernail polish, so you can use that. Now, the other thing is we want to measure the amount of caffeine extracted from the coffee bean. Now, I found these two articles. This is actually a scientific paper, measurement of caffeine in coffee beans with a UV visible spectrometer, which is what we have in the lab. And then I found another article. This is from Separation Science. This is a company which actually makes UV visible spectrometers. And if you can see this, you can't see it too well. This is the absorption spectrum of caffeine. And it shows a peak at about 275 nanometers. When you showed me your absorption spectra from lab on Tuesday, wasn't your peak at around 280 or 270 nanometers? Yeah, so that means that the substance that you were looking at, which gave this absorption peak, must be caffeine. That's what you're looking at, caffeine. Okay. Rolando.
So you got that working?
I did a search. I think for my Google search, I looked up absorption spectrum of caffeine, and I found this article. Anyway,
the actual spectrophotometers, they were able to detect.
Yeah.
Oh, okay.
I think for this spectrophotometer, they went from 150 to 1,000 nanometers. Our spectrophotometer goes from 200 to 850 nanometers. So
I remember we had all that noise. So
yeah.
Really
I think that noise is from the cuvette. Although I'm not sure, because what we can do in lab, we can run a UV spectrum just of the cuvette and see what it looks like. Okay, now another way, I found this, another way to quantify the amount of caffeine is to do an HPLC analysis. So we actually have an HPLC in the lab, which we haven't used yet. So we should get the thing fired up so you guys can use that. So HPLC stands for high performance liquid chromatography. So it's actually like a type of extraction technique. So what happens in chromatography is okay, so this is true for any chromatography experiment. There's two phases. So one phase is the moving phase. This could either be a liquid or a gas. The second one's a stationary phase, usually a solid. So in a liquid chromatography experiment, you have this tube or this pipe, and you have the solid deposited on, this is a solid. You have the solid deposited in this tube. Then you have this liquid flowing over or past a solid. Okay, so it turns out that if you have a mixture, some of the mixture will be more attractive to the solid than the liquid, or the other way around. So that's how you can separate a mixture by using chromatography. Okay, so in chromatography, one mixture will be more attracted to the moving phase, the other component will be more attracted to the stationary phase. That's how you can do the separation. So that's what's happening in this HPLC experiment. And then here's the structure of caffeine. So again, if you look at caffeine, note that there are some oxygens and nitrogens, and since there's oxygen and nitrogen present, can hydrogen bonds form from water to caffeine? And the answer is yes. Okay, so that's why caffeine is soluble in water. Okay, so keep this in mind when you're finishing up with that up in lab. And then what you'll also do in lab today is we're going to measure the amount of CO2 in soda, and we'll discuss this problem, problem 13.107, using Henry's law. This is actually a pre-lab question. Then we'll figure out how to measure the gas pressure in a soda can. Okay, so you'll do that too, either today in lab or next Tuesday in lab. So since it's Thursday, let's take your next quiz. Now let me write down the picture from problem 13.85 in the textbook. And this is for this time-release drug.
Excuse me, do you know where's Brian Montgomery?
Is he a student or instructor?
Instructor.
What class?
Astronomy. He teaches in this class at 6 o'clock today.
I don't know who he is. Since it's,
Okay. Well, I'll come back later, like, right after class.
okay, so for question 1, you want to explain how this time-release drug works. I'll write it on this side of the board too. And for question 2, explain what happens when a can of soda is open.